When you're given an initial concentration of the weak acid, which is 0.10 molar in this case, and you're given a pH, here's what you want to say: thank you. Because calculating the Ka when you're given these two values is pretty simple. Now, in general, calculating the Ka of a weak acid is like any other equilibrium calculation. The first thing you need is a balanced chemical reaction. In this case, we have this weak acid, which only partially ionizes in solution, and so it sets up an equilibrium. So I'm going to use HA for my weak acid as sort of a generic monoprotic weak acid. And that makes my life pretty simple, because if it were acetic acid, I'd be writing HC2H3O2 or HNO2 for nitrous acid. But HA is a nice generic monoprotic acid because what you find out is they're all the same. And you know how it is when you're calculating a Ka and you're not given all the information you need in terms of the equilibrium concentrations. You need a nice table to make sense out of the information. So here we have 0.10 molar initial concentration of our weak acid, our initial concentration of our two products, H plus and A minus, or 0. That one kind of looks like a football or something. Our change is going to be minus X, because the coefficients are all 1, and plus X for our two products. And then we simply add the initial line to the change line, and in the case of the weak acid, we're trying to calculate the number of molecules of our weak acid that remain after the equilibrium has taken place. Now, you're absolutely right. I know you were thinking this. Add the initial to the change line. This should be X. But they've given you the X by giving you the pH. So here's how you get it. If you remember that pH is simply equal to the negative log, log, that's the log base 10, of whatever the hydrogen ion concentration happens to be. Now, this is also known as the common log. It's log base 10, the log. Make sure that you use that instead of the natural log, which is ln. I can get the X value, which is the hydrogen ion concentration, by simply taking the negative antilog of the pH. And when I take the negative antilog of the pH that's given in this problem, which is 2.38, I get a value that's equal to 4.2 times 10 to the minus 3 molar. So that's my concentration of hydrogen ion. And since it's 1 for 1 with the anion, it's 4.2 times, come on, times 10 to the minus 3 molar for hydrogen ion. It's also 4.2 times 10 to the minus 3 molar for the anion. Now, like any other equilibrium constant calculation, I want to go ahead and write my equilibrium constant expression using my products, H plus, let's make that a little better, times A minus in this particular problem, divided by my HA concentration. Now, I know my concentration of H plus and I know my concentration of A minus. They're on the equilibrium line of my ICE table. What I don't know yet is my equilibrium concentration of HA. So it may not make a difference, but let's go ahead and be very accurate and calculate the equilibrium concentration of HA by taking the initial concentration, which is 0.10, and subtract X. Well, we know what X is. X is 4.2 times 10 to the minus 3. And when we do that, we get a concentration of our acid, our weak acid that remains in solution after equilibrium is established, of 0.958 molar. Now we're ready to go ahead and calculate our Ka. We plug in our 2x values, which is 4.2 times 10 to the minus 3 times 4.2 times 10 to the minus 3, which is just 4.2 times 10 to the minus 3 squared, divided by our weak acid concentration at equilibrium, which is 0.958, and we get a Ka that's equal to 1.8, where did it go, times 10 to the minus 4. And that, my friends, is our answer. So I hope you had fun doing it. I hope you learned something from it. And we'll do another problem a little bit later. Take care. Learn.